So our speaker tonight, Dr. David G. Stork, epitomizes the C.P. Snow spirit. David is chief scientist of RICO Innovations. The breadth of his interests and contributions is revealed through the academic departments and programs in which he has held faculty positions: physics, mathematics, electrical engineering, statistics, computer science, neuroscience, psychology, and art history, variously at Wellesley College, Swarthmore College, Clark University, Boston University, and Stanford University. He is a fellow of the International Association for Pattern Recognition. He's written 8 books, has 40 patents, and has made over 220 scholarly presentations on computer analysis of art in 17 countries, including in major museums such as the Louvre, National Gallery London, Metropolitan Museum of Art, and many, many others. So we're happy to have him come speak to us tonight. Please join me in welcoming our speaker, David Stork.
Thank you ever so much, Janet and committee, and for all of you for coming, and congratulations to Marissa for following in footsteps laid out by C.P. Snow himself. Well, the wealth of visual information that we get from art is astounding, and it's really been, to me, somewhat surprising that it's been only the last few years, and only from a handful of us worldwide, that we've been applying techniques from computer vision, the branch of computer science trying to make computers see, to understanding several problems in the history and interpretation of art. And let me give you some examples of what we've been able to do. Let me start with Vermeer's Girl with a Pearl Earring. Vermeer was well known for his mastery in rendering the effects of light. Look at the subtlety of the shadow on her cheek, the reflection off the pearl, the glint off her moist lips and her eyes, and so forth. But if we were to ask the simplest technical question about the illumination in the painting, it would be this: what's the direction of illumination? Well, and if two connoisseurs disagree, how would we tell which one is right? Are they equally valid interpretations? Well, let me show you 6 techniques from computer vision that answer this question absolutely clearly. Then I'll tell you how it changes our understanding of this painting, of how Vermeer worked, and how these techniques can be used elsewhere in the history of art. There are 2 general classes of methods. The first are model-independent methods. These are methods that don't require us to know or assume anything about the 3-dimensional form of her face. We'll look at a cast shadow cast in the tip of her nose, and the occluding contour algorithm, which I'll explain. And then the model-dependent methods do require us to know something or make some assumptions about the 3-dimensional form of the objects in the tableau. So we'll look at the pearl, 3-dimensional model of the pearl, of her eye, of her face, and we'll make a full 3D computer graphics model. So the simplest is cast shadow analysis. You take a point on an occluder, like the tip of her nose, the corresponding cast shadow point, draw a straight line between those with error bars, and we find that the direction to the illumination from this estimate is about 150 plus or minus 2 degrees, where we're going to measure our angle with respect to the horizontal. Now, the occluding contour algorithm, don't worry, there's going to be some math, there's no test. But I want you to get a feel, at least, for the kind of mathematics that goes on in these new methods for understanding art. The occluding contour algorithm is based on a branch of computer science called shape from shading. It tells us that the brightness of a point on a surface, like a cloth or dry skin, we call it a Lambertian surface, is determined by 3 things: the overall intensity of light, which we'll set to 1. The reflectivity or albedo of the surface, is it black, or is it white, or is it gray? And then the angle that the surface makes with respect, that part of the surface makes with respect to the light. We describe that by the normal vector, a line perpendicular to the surface, and then there's the, for us, unknown direction to the illumination L. So in vector components, this is the formula. The problem is, for this painting, we don't know what the shape, 3-dimensional shape of her face was. We don't know what the normal is. So 2 computer vision experts, Nilius and Eklund, came up with a very clever insight on how to solve this problem. They said, all right, we don't know what the normal is on an arbitrary point, but around the outer boundary, or occluding contour, we do. Think about it. We might not know what the normal is here, but as we get to the outer boundary, the normal must be perpendicular to your line of sight that is to say, in the plane of the painting, and perpendicular to the contour itself. So I know for sure that the normal is like this here, it's like this here, it's like this here. I might not know what it is here. So that means the equations are much simpler. Why? Because the normal vector does not point towards you or away from you. It's perpendicular. It's kind of like a flagpole on the horizon of the Earth. And so its z component is 0. And we also can measure exactly what the components of the normal are. So I know what the normal is here, here, and here, even though we don't yet know what the components of the direction of light are. Well, I won't go through the math anymore, but there's a set of linear equations that will allow us to estimate the direction to the light based on the pattern of lightness on the outside. So here's one way to see it. Imagine we have a three-dimensional object, and I measure the brightness of the patch along the outer boundary here. That's determined by three things: the overall intensity of light, the albedo, and this unknown angle to the illumination. So if I just tell you that one number, you have one equation and three unknowns, you just can't solve it. You remember that from high school. But if I measure three or more, then I can. Look at this bright patch. It's probably facing towards the light. Look at this dark patch. It's probably facing away. And all that mathematics I just went through takes all of these measured lightnesses and says, what direction to the light best explains all of these, this pattern of lightness in a sum squared error sense. Well, this technique was actually developed for forensic photography. Here's a photo of Brad and Angelina. There was a time when one of these photos sold for $500,000. And then, not to be outdone, the Star made this photo, or had this photo on its cover. And a friend of mine applied the including contour algorithm to Brad and found that the light was coming from this direction. Ditto Angelina found the light was coming from this direction. This was Photoshop, or as we say, tamper. And this including contour algorithm was one way to determine that it was a fake photo. No wonder Jen was shocked. We were the first to ever apply this to paintings. So the computer takes the lightness measured along this outer contour and puts in that yellow line as the direction. It turns out to be about 149 plus or minus 4 degrees. Now, I've asked distinguished connoisseurs if they can do it by eye, and they're very poor at being able to estimate this angle, not nearly as well as our computer methods. Now for the model-dependent methods. I took a very high-resolution photograph of the pearl in the painting in the Mauritshuis Museum in The Hague, and I sampled 14 points along the outer boundary, or the occluding contour of the pearl, and we can confidently assume that the pearl is a cylinder, so I could then make a three-dimensional model of the pearl. This is a wireframe computer graphics model. And then we have to texture map. We have to add the surface to it. So here we go, we add on the white. But a pearl is not diffusely reflecting like cloth. It has a specular or mirror-like reflection on it, like this. And so you have to adjust by eye the relative components of the diffuse reflection and the specular or glassy-like reflection. And so that's what you have here. And now we can adjust the position of the virtual illuminant in this tableau virtuelle anywhere we want until the rendered pearl matches that in the painting as closely as possible. And that's what this is. And now we know the direction for the estimated direction for the illumination. Turns out to be about 155 plus or minus 4 degrees. Now, what about the glints off her eye? Well, if the eye were a sphere, of course it's not, but if the eye were a sphere, the position of a glint or a highlight on the eye is related to the direction to the illumination by a very simple formula. You've probably not seen it in this formula. Really, all it is the law of reflection. The angle of incidence equals the angle of reflection. But of course, the eye is not a sphere. It has this corneal bump that pushes out. And if we're going to do this kind of analysis, we have to know which way that bump is pointing. So we took an oval and fit it to the outer boundary of the iris, or colored part of the eye. And in this painting, just so happens that that oval is a perfect circle, meaning that she's looking directly at us, or really directly at Vermeer. And I hope some of you can see the little green dots in the middle of the highlights. That's where the computer finds the center of mass of the highlight. So in the computer model, if you will, the eyes are looking straight at us, or at Vermeer, and the highlights are here and here. And it's high school optics, once you have a model of the eye, to estimate the direction of illumination. Turns out to be about 150 plus or minus 2 degrees. The most sophisticated and difficult technique we use goes back to that idea of shape from shading. It works this way. If we had a three-dimensional model of her face, then we could say, well, what position of an illumination for that model would lead to the appearance that we find in the painting? But again, we don't have a model of her face, or we don't have Scarlett Johansson to come in and pretend to be her or something. So you did the next best thing. You took a computer graphics model that's used in a lot of computer graphics research. It's actually of a man's face. We adjusted the pose to match the face in the painting as closely as possible, and we temporarily assumed that was her face. So we said, all right, for this model, what position of illumination will lead to the appearance that we find in the painting? And that gives us an initial estimate for the light direction. But again, it's not going to be correct, because this isn't the correct face. Then we took that direction, and we held it fixed, and we said, all right, now let's fix her face, so the computer can change the size of the nose, shading, and so forth, the albedo, the reflectivity around the face, and so forth. And that gives us a better model of her face. And we take that better model, and then we re-estimate the direction to the illumination. We go through this just twice, and it settles down. And at the end, we have a direction to the illumination. It turns out to be 160 plus or minus 5 degrees. Then we made a full 3D computer graphics model of her face. I know it looks a little bit creepy. Computer scientists actually have a name for it. It's called the uncanny valley, when something is not good enough to fool you into being human. And when I showed this at the Maritz house, where this painting hangs, the conservators went crazy because they'd never seen the back of the painting. So we can now take this and we can put the light anywhere we want, and we're going to stop it in the configuration we think best matches that in the actual painting. And then we're going to fly around Vermeer's studio to see what she would have looked like from different positions. Now, this method is formally ill-posed. That is to say, we have to make some assumptions about her face. So for instance, we assume that her face is bilaterally symmetric. We don't know that for sure, but we assume it, and that turns out to be acceptable because it adds noise or adds variance to our estimate, but it doesn't add bias. When we assume her face is bilaterally symmetric, that doesn't mean the light's going to be too high or too low. It just adds noise to it, so to speak. So now we're going to stop the movie in the configuration we think best matches the painting, and we're doing what's called an alpha blend, basically a blur into the actual painting, and it matches really quite well. And so now we have our estimate, another estimate to the direction of illumination. So here are some stills from that movie, if you will. I won't take your time, but this one best matches the painting. This is a little too low, and this is a little too high, and in that way we get an estimate to the direction of the illumination. All right, so we've estimated the direction of illumination 6 times, 6 different ways. How well do they agree? Here are our results. Here are the methods. Here are those angles, and the average of these turns out to be 155 degrees. That's not too important. But what is important is this very small standard deviation, showing that there's great agreement among these 6 different techniques. Here's one way to visualize it. The red line is that 155 degrees. That's the direction to the illumination. And the yellow line is a cardioid, because it, believe it or not, actually has a heart-like shape. But it's so stretched out because those methods all agree so well. What the yellow line shows is the relative probability of finding the light in a given direction given all this evidence. So it's most likely the light's in this direction. It's only, about 50% as much if you go off in this direction. So the fact that this yellow curve is so drawn out and elongated shows that there's great agreement amongst these different techniques. So that's a testament to Vermeer's ability to render light in these different methods, as well as a testament to the accuracy and the precision of our methods.